Advances in our ability to nanostructure electromaterials has given rise to the exciting new field of nanobionics. Advances are realised through a detailed understanding of material properties and the development of innovative approaches to fabricate devices from these materials. The common battery is an excellent example, materials that store charge, effectively assembled into a practical device. Even for these rather conventional materials, we uncover exceptional properties as we go from the macro to the micro domain. Here, electrochemical processes are inherently more efficient. As we venture further to the nano domain, exceptional properties become extraordinary. The ability to transfer charge from one system to another can be dramatically improved. The ability to transport charge within a structure is greatly influenced, with conductivity values improving by orders of magnitude. Enhanced surface area ensures high-performance electromaterials. Accompanying these enhanced physical properties are changes at the molecular level on nanostructured surfaces that determine how proteins and cells interact. As a cell approaches a foreign body, such as an implanted electrode, the tendency to become intimately involved depends on both the composition and the structure encountered at that electrode surface. We have been particularly interested in novel compositions based on organic conducting polymers. These possess dynamic properties controllable by electrical stimulation, and this includes the ability to tune surface energy and mechanical properties, as well as to initiate localized release of bioactive molecules. We can therefore tune the surface to be highly receptive to selected cell types for a range of applications. We will now consider some of the clinical applications where nanotechnology is having an impact on medical bionics. The cochlear implant, invented by Professor Graham Clark, relies on electrodes to transmit electrical stimuli from an external microphone. Sound is transformed into electrical impulses delivered to nerve cells. As we decrease the size of the electrodes into the nanodomain, we can provide more sites of electrical stimulation and more effective bionic hearing. Our ability to fabricate nanostructured electromaterials that support and facilitate cell growth opens up the possibility of developing a conduit for reconnecting severed nerves. We have recently demonstrated that nanodimensional topographical cues can be used to control the direction of neurite outgrowth. This provides a platform for nerve regeneration or for coupling nerves to a neurally driven prosthetic, such as a robotic hand. A number of diseases and, of course, trauma can lead to muscle loss and a need for muscle regeneration. We are developing electromaterials that provide an environment for muscle cell growth. Nanotopographical features on these platforms direct the assembly of the individual cells into muscle fibers and tissue. We envisage that this regrown tissue can be transplanted into an environment where muscle regeneration can occur. Epilepsy affects 1% of the population, and 1 in 3 of these individuals are untreatable using conventional approaches. We are involved in the development of nanostructured electromaterials as a critical component of an implant for epilepsy detection and control. We propose to develop an implant that will be capable of detecting brain signals that provide a warning of an impending seizure. Integrated into that implant will be a nanostructured polymer network that functions as a reservoir for anti-epileptic drugs. Coupling the electronic warning system using electronic signals arising from the brain will enable triggered release of the drugs when and where they are needed, hence preventing seizures from occurring. The bone-cartilage interface may be damaged through trauma, removal of tumours, or through diseases such as arthritis. Rebuilding this interface poses a challenge that may now be overcome due to recent advances in micro and nano fabrication. Diseased or damaged tissue can be removed using appropriate surgical tools. A 3D scaffold that fills the defect and provides an environment for cell growth is then installed. This implant is rather sophisticated. It consists of 3 layers with a composition and structure appropriate to encourage bone regrowth, cartilage regeneration, and the effective integration of both. In the bottom layer, immediately adjacent to the bone, seeding with osteoblast cells assists with bone regeneration. Seeding other layers in the scaffold with osteochondral cells and chondrocytes then enables production of extracellular matrix molecules, such as collagen, that are needed to rebuild cartilage. Cells continue to fill the scaffold, producing extracellular molecules, ensuring reconstruction of cartilage and the bone-cartilage interface. We will utilize electrical stimulation of nanostructured electrodes strategically positioned within the scaffold to facilitate the regeneration process. The ideal outcome is complete repair of the damaged site with functional cartilage. In this application, control over the spatial distribution of composition and structure in 3 dimensions is critical. Progress in each of these areas of clinical application has been made possible by advances in nanotechnology. There is no doubt that as we continue to progress the field of nanofabrication of organic molecules, a powerful new material platform will be available for medical bionics. The exciting era of nanobionics will have a significant impact on clinical applications.